Okay, let's start our seminar. First of all, I forgot give you some exercises. No, one exercise, it's important exercise for the future. About regular sequence. If you have commutative ring and you have ideal finitely generated by some finite regular sequence. Now then please calculate Tor over R between R modulo I and R modulo I, and check that this is isomorphic as R modules, for example, to exterior algebra of I modulo I squared. No, what is exterior algebra? This is R module, yes. Now if you have R module exterior algebra, no, it's graded algebra. No, something you consider something like tensor algebra, yes. And then consider quotient modular ideal generated by tensor squares of any elements. No, ideal generated by, this is associative algebra, no, R algebra, yes, some ring. And you consider it's not commutative. And you consider two-sided ideal generated by elements from this of squares. Yes, and this is extra algebra. No, and you can check that this is isomorphic things. For example, we checked some time ago, we checked that if you have two different ideals, no, it's true for any ideals. And you consider Tor1, yes, you obtain something like this, yes. Now, if I is equal to j, then this is I modulo I squared, and this is exactly the same. No, this is true always. No, this is for simplicity for regular ideals. It's exercise not. No, it's simple enough to give you now, but no, it's important for the future about for Homological homology. Maybe if we will discuss them. No, this is kind of in algebraic geometry setting. Yes, this is tangent space, and this is differential forms. Yes, and this is Tor. It's a homological interpretation of some kind of Theorem algebra. If your algebraic variety, it's kind of normal intersection, is ideal of some regular sequences, intersection of some regular hypersurfaces, kind of. Okay, no, this is algebraic exercise. Okay. Так. Then what about formality and about algebras? First of all, maybe Misha, do you know the example of algebra which has no quasi-isomorphic to something but has no quasi-isomorphism in the opposite direction? We have algebra and another algebra, differential graded algebras. And no, I claim that there exists example of two algebras where we have quasi-isomorphism in one direction, but we have no quasi-isomorphism in another direction. No, so when we are overfilled. So in chain complexes, no, there are no such examples because in overfilled quasi-isomorphism is the same as homotopy equivalence, and there are no theory here. But if you consider multiplication, then it's important. So quasi-isomorphism is zigzag. But no, yes. Now here I think we have a simple example, and its example is from homotopy. Let's consider something like the homology of even-dimensional sphere. It's algebra something like x modulo x square, yes, and x in dimension, in some even dimension. It's commutative algebra, and so, but it's not minimal. we have minimality definition in the previous one also. But what I want to say is that then it has a minimal, minimal model, yes? And what the minimal model of this algebra? Algebra is minimal if it's free. It's generated by extra algebra of odd dimensional generators and polynomial algebra of even dimensional. No, and such that you have ordering of your generator such that differential of any any generator lies in ideal generated by previous numbers. Then such algebra is called minimal in the sense of Sullivan, and for any algebra you have quasi-isomorphism from minimal unique. You have a unique up to isomorphism minimal model in commutative case. It's commutative algebras. No, and we have some theorems. For example, yes. No, so what the minimal? I want what the. I don't say. Sorry. Not this algebra. It's kind of chain algebra. I want that it's homology. It's homology of sphere. So I want to say that something like. Maybe. It's okay. Yes. No, differential is also 0. Yes. No, this algebra is not minimal because this algebra is not free. This generator is even, but this is not polynomial and even. So we have some relation. And I want morphism from minimal algebra such that it's isomorphism on cohomologies. What the minimal model of this algebra? It's kind of minimal model for even dimensional sphere. For odd dimensional sphere, we obtained something like this. And this is already minimal. But for even dimensional, it's not minimal. But we have minimal model. No, we have something like this. So I think we need to have something like x here in dimension 2n. And it must be cocycle. Yes, it's cocycle. Okay. But then it's polynomial. We have x squared, but x squared must be here differential is 0, so it's also cohomology. So in cohomology, this is square of this cocycle must be 0. Yes. So I have x squared. It's not 0 in this algebra, but it must be 0 on cohomology because cohomology of this algebra is the same thing, and it must be isomorphism in cohomology. Yes. So in cohomology, the square of this cycle must be 0. Okay. So it must be coboundary of something of dimension -1. So I need to add this thing. And this is then it's okay. This is a rule of my differential. This is minimal algebra with this number 1, 2. Differential of y is polynomial in previous generators. It's free. And I have morphism of algebra when x goes to x, and y goes to 0. And this isomorphism on homology, because homology of this thing is exactly this thing. So this is quasi-isomorphism. But I think we cannot construct quasi-isomorphism in the opposite direction. Yes? No, because I have only one 2n-dimensional element here. It must be go to something 2n-dimensional, but no, its square is 0. Square of x is not 0 here. Okay. I even cannot define homomorphism of algebras in the opposite direction. No, not 0. Something like x goes to. For any algebra homomorphism, x must be go to 0. Something like this, because x squared goes to 0, but here it's polynomial algebra. And by dimension reason, yes. x goes to something like alpha x, no, x squared goes to alpha squared x squared. No, maybe consider, I don't know, characteristic 0. Yes, and then it's not 0 even only if alpha is 0. And then it's over any field. Yes, alpha squared is 0 only if alpha is 0. Okay, so any ring homomorphism in the opposite direction sends x to 0, and this is not isomorphism homology. Okay, do you agree? So that's a free example. It's example of, and this no, it's prototypical example. We have something non-minimal. We have minimal model. No, it's a rare situation when we have quasi-isomorphism to minimal model in the opposite direction. In general, we have two algebras. If they commutative, then this means that they have the common minimal model, and we have two quasi-isomorphisms. But of course, in general, we don't have quasi-isomorphism in the opposite direction. Okay. Okay. The next example is the example of not formal algebra. Yes, I said it before. Consider lambda x, y, z. They all of dimension 1, but numbered by this in this order, with differential x, y, 0 and dz x, y. And then this algebra is minimal. And I said that this algebra is not formal, so I don't have quasi-isomorphism. This algebra, not zigzag of quasi-isomorphism, not quasi-isomorphic to its homology with 0 differential. So it's the example of not formal algebra. Not any algebra is isomorphic to its homology. Now, for example, if we have quasi-isomorphism, this algebra is minimal. So as I said before, and it's commutative, and homology is also commutative. So as I said before, if such quasi-isomorphism exists, then this means that this A is minimal model for this algebra. This algebra maybe is not minimal, but this algebra is minimal. If you have some algebra and some minimal algebra and they quasi-isomorphic, this means that this minimal algebra is in fact minimal model. And this means that in this situation, if you have minimal algebra and some algebra and they quasi-isomorphic, this equivalent to say that there exists quasi-isomorphism in this direction, from minimal to algebra. Maybe not in the opposite direction, but in this direction. So if it's true, and from minimality, it's from not very obvious Sullivan theorem, but we did not prove this. But it's from Sullivan theory. If you have minimal algebra and quasi-isomorphism, then in fact you have quasi-isomorphism from minimal algebra. No, in fact, this fact is not very hard. No, because it's minimality. It's free and differential. It's decomposable, and so you can define this quasi-isomorphism by induction on generators. In fact, you have algebra minimals, you need to go generators to some cocycles, and differential defined by induction, something like this. So in fact, this is not very hard, from minimal to algebra by quasi-isomorphism. Okay. No, in fact, what I want to say, if you have, okay. No, so you need to check that if you have quasi-isomorphism in the opposite direction, then you have quasi-isomorphism in this direction. Okay. Okay. So why this quasi-isomorphism cannot exist in this situation? So it cannot exist quasi-isomorphism relative to its cohomology.
Perhaps we should say vice versa. We have quasi-isomorphism from A to minimal model, then we automatically have quasi-isomorphism from M to A.
I think yes.
Then,
but maybe we don't have. No, it's from zigzag. If you have, for example, zigzag, yes, then in fact you have something like this, and infinity. Maybe you have no this direction, I guess. What I said before is if you have zigzag, then in fact no, you can switch direction of arrows from minimal model to something. No, it's I think it's not very hard, but no, it's true. What's your question? No, it's not true that you always have map to minimal. It's not true. No, minimality it's kind of free in the minimal. So it's easy to define maps from a minimal model. Okay. You only need to define its own generators in such a way that it respects differential, and it's not very hard by minimality. Okay. Here. For example, here I have two cocycles in dimension 1, x and y, and its multiplication is 0 in cohomology. So here I have what? Let me define x and y. It's corresponding cocycles in dimension 1, and in fact, in dimension 1 I have no other homology classes. Yes, because in dimension 1 I have only x, y, and z is not a cocycle. Okay. So in fact, first cohomology, it's vector space generated by these two cocycles. So if I have such map F, then it must sense x to something like of this form, and y something like this form. But then, what I want to say, then where goes, for example, what I want to say? No, it's not. Sorry, it's true, but it's not important. No, not. Sorry, this is okay. For example, they must go. I consider z. Z is some element from first grading of this algebra, and it also must go to some first grading of this algebra. So the z must go to alpha x plus beta y. Whoa. This cannot be happen, in fact, because if you consider then zx, no, this is a homomorphism of algebras, so it goes to alpha x plus beta y. No, x. This is zeros, because x square is 0. Because it's algebra. X square is 0. Yes, we have all these elements. X square is 0. X square is 0, and xy is also 0 in homology. So multiplication of classes xy is also 0. So it's 0. And what is zx? Differential of zx. What is differential of zx? Is differential z? No, x is cocycle, so in fact it's differential z on x. But differential z is xy, so it's xy x. No, this is 0 because x squared is 0. So this is cocycle, and this cocycle is not coboundary. You can check that you don't have coboundary such that it's coboundary that x is not coboundary. So it's non-trivial homology class. But we see that this cocycle goes to 0. So this is not isomorphic on cohomology. This cocycle goes to 0, and this is not 0 in cohomology of my algebra. So it's contradiction. So this algebra is not formal. What? No, and in fact you can, for example, pick some non-trivial Massey product, triple Massey product. What this zx? It's kind of Massey product of form. No, I think something like this. X, y, x. Yes. Or maybe no, x, y. What? Or maybe in fact x, y, y. No, x, y, y. Sorry. No, it's not important, but no, I want to consider something like this class lies in this Massey product. What is Massey product? Yes, you want to ask. Do you know what the Massey product is? No, then you should. Huh? No, yes. For example, so we have some argument, but also, no, this is more or less. Как это? More or less. В одну цену, in one price. To check this argument and or consider some find some non-trivial Massey product. So for example, yes, here we have xy is dz, yes, and y squared is 0. So it's, for example, d0. So by definition, we have no xz, no modular signs. It's this thing, yes. So sorry. And as I said before, this is non-trivial class. No, sorry. Yes, it's non-trivial. But why this Massey product is non-trivial? Sorry, it's not this. No, in fact, this Massey product is uniquely defined, I think, because no, it's not maybe not uniquely defined, but no, okay, okay. Xy must be d of something. D of what? No, it's d of some one-dimensional class. It must be z, no, plus any element from this, because all the differentials to 0. Okay. Y squared, it's 0. It must be also d of something one-dimensional. No, it's also of this sort. No, okay. If I define, this is all defining system from this triple Massey product. If I define Massey product, then I obtain what I obtain. I obtain z plus alpha x plus beta y y. No, maybe yes, with sign. Yes, in differential graded algebra, if element is of degree n, then a bar is -1 n plus 1 a. And for example, triple Massey product, if you have 3 elements, A, B, C, and you know that in cohomology, this multiplication, these products are 0, then you can choose some cocycles, some boundaries of these differentials. And then you can consider something like xc plus ay. And you can check that this is cocycle. And the set of all such cocycles is some set of cocycles of cohomology. This is lies in cohomology. And this is called Massey product of these 3 cocycles. If you have 3 cocycles such that these pairwise multiplications are 0, then you can define this map. And you can check that if such Massey product called trivial if it contains 0. If you can obtain 0 in such a way, you can say that this Massey product is trivial. And you can check that if, and also you can define n-tuple Massey products, in fact. And you can check that if your algebra is formal, if it's quasi-isomorphic to cohomology with 0 differential, then all Massey product is trivial. So, for example, example of non-trivial Massey product is the abstraction to formality of algebra. And here, I consider these 3 elements. xy is 0 in cohomology, y is 0 actually. And I want to find any elements, any cocycles. Any cocycle which, not cocycles, any cochains, any elements. Any element such that its coboundary is xy is z plus something, with cycles. Any element in dimension 1 which is differential 0 is something like this. So I define now Massey product of this any element. I want to check that this Massey product is non-trivial, so I cannot obtain 0 by in such a way. No, indeed, in cohomology, 0. No, indeed, I have this, and then I have x. Not this. And then I need to consider cohomology class of this. No, here in cohomology, xy, y squared, and x squared are 0. So in cohomology, it's just class zy. Oh, why? I wanted zx, yes. Ну, ладно. Ну, zy, okay. No, this is zy, and this is not, this is unique element. So in fact, this Massey product is not, как это? No, it's not multiple valued, it's unique valued. It just contains only contains only one element, exactly zy. And this is non-trivial element, no, by the same argument. So this is more or less the same thing in this easy situation. No, in general, it's not enough. You can construct some algebra which has all Massey products are trivial, but it's not formal by some different reason. But no, this is some abstractions for this. For example, if you consider Kähler differential, then differential forms of Kähler differentials are always formal. This means that Kähler differential is formal. Manifold is formal. Its Theorem algebra is formal. It's quasi-isomorphic as algebra to Theorem homology. And for example, Kähler differentials are formal. It follows from D bar lemma. No, you can see this. I don't know, 2 weeks, in 2 weeks on teaching. Okay. 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 Ну вот maybe, ну да, maybe, and yes, and the main theorem about this, as I said before, no, in fact, it's the following theorem. If we have quasi-isomorphism of algebras, then on Massey products, all n-tuple Massey products, it's X by bijection. And in particular, if you have, no, and also easy exercise, if your algebra 0 differential, then all Massey products are trivial. So if you have zigzag of quasi-isomorphism such that on the end you have homology with 0 differential, then in fact all Massey products are trivial. It contains 0 because they are the same as at the end, and at the end they are trivial. So from this we obtain that non-trivial Massey product, then A is not formal. Now maybe let's check this thing for triple Massey product. No, for n-tuple Massey product it's the same argument but more tedious calculations. Let me check this for triple Massey product, for example. No, не вот это. No, as we said before, it's obvious this inclusion, because any defining system of this thing, if you have any Massey product, if you apply f, you obtain defining system for this Massey product. So all these images contained in this Massey product. Okay. So what we need to check is the opposite inclusion, something like if this is true for any homomorphism of algebras. So our argument is about if we have quasi-isomorphics, then we have something like this. For any ABC such that we have this Massey product. No, if we have this Massey product, if this Massey product defined, this means that multiplication of classes is 0. Then multiplication of this class is also 0 because it's f is quasi-isomorphism is homomorphism of algebras, yes. And if we have AB 0, then f it's also 0. Okay, on homologies. So this Massey product also defined, and we only need to check that any element of this Massey product can be lies in this. It can be obtained as f of some element in Massey product ABC. Okay. So, yes, but let's start. We have defining ABC. So we know that AB, for example, is dx, and BC is dy. It's in A. And also we consider any element class Z here. This is the question. Yes. No, sorry. No. This, yes. I have this. I have any element. I have some cocycle. So this element is by definition is something like x f c plus f a y. Yes. Okay. Yes. It is. I think this is exactly Z. Okay. But also I have defined a system, for example, for AB is alpha, BC is beta, D alpha, D beta. No, really alpha. No. It's just simplicity of notation. Yes, and I have that. No, what this definition? I have f alpha is dx, f beta is dy. No. No. Yes. Not. Yes. I consider some cochamp. Sorry. Yes. Then I obtain that. What I obtain that d of f alpha minus x is 0. Yes, and d of f beta minus y is 0. Yes. No, I choose any defining system for Massey product ABC, and I have this. Yes. It's cocycles. So as it's cocycles, it's some cohomology classes, and because F is quasi-isomorphism, it's isomorphism cohomology. It's image of some cocycles modulo some coboundary. So from this I obtain that F alpha minus x is F of some cocycle plus some coboundary. No, and F beta minus y FB plus DV. Oh, it's because F is quasi-isomorphism, surjection on homologies. Okay? No, and now I redefine my defining system for ABC. I consider something like alpha prime is alpha minus A, and beta prime is beta minus B. So because AB is cocycles, differentials of alpha prime and beta prime is the same as AB and BC. So it's also defining system for ABC, because I add some cocycles. It does not differ my differential. Also, what I obtain if I consider the corresponding Massey product and apply F? No, I have something like this. Okay, I have something like that, and I apply F. This contains in ABC. No, it's homology class, and I apply F. It contains in this. But what is it? No. F alpha minus Fa, it's x plus du. So it's f of x plus du c plus f of y plus dv. homology class. No, and now C is cocycle, this is coboundary, so this is coboundary. This homology class doesn't depend on this summand, and also this is coboundary, this is cocycle, also doesn't this homology class doesn't depend on this summand. So this homology class exactly equals to fx c plus a bar fy. So this is exactly my z. So I represent my z as f of some homology class of my Massey product. No, and more or less the same procedure of redefining defining system, but of course in some induction or in some n steps works for n tuple. Okay? Does this make sense? No, so I have some defining system for this, some defining system for this. They are arbitrary, so they maybe do not coherent. But I can redefine some twist my defining system for A, B, and BC to obtain what I want to obtain. Okay? And for n tuple, it's much more of such steps. Okay. So from this follows that, for example, yes, and we also need to check that again, but it's easy exercise. You can even do this. By definition of triple Massey product, you can check that if you have zero differential, then any triple Massey product is zero. And from this, we obtain that if A is formal, then any at least triple Massey product is zero. And in our previous example, we have non-trivial triple Massey product, so this algebra is also not formal.
Why is it class of C?
Of Z?
You wrote.
Of Z?
Yes.
Или C? I did not. No, because this Z is by definition this thing. No, Z is by definition some Massey product, so I need to check some. I need to choose some. Some cycles of f and b, and then by definition this f elements for some x and y. Yes.
Yes, I understand, but they are different. F of x.
It's different. Sorry. Then I think because I write it not correct. Sorry, because f alpha plus fa is x. Is x, and this is y. And then I apply, yes, and then I apply f, so this is x, and this is fc. Sorry, yes, you're right, and fa. Here I apply f to this and to this. This is fc, and this f alpha minus fa is exactly x plus du. Yes, you're right, you're right. Sorry. You're right. It's true, it's just a typo. F of this difference is x plus something, and fc, and some coboundary. Because of this sort. F alpha minus fa is x. Yes, you're right, sorry. Okay. Now maybe about topology. About applications of element pure spectral sequence. Actually, I recall what is element pure spectral sequence, any at least formulation of the, yes. As I said before, if A is DGA over any ring, here it's not important that we over a field. It's over any commutative ring. But connected, non-negatively graded, and so on. Non-negatively and connected. A0 is our ring. And two differential graded modules, also non-negatively connected. Then non-negatively graded. Then we have a Moore spectral sequence. A spectral sequence of the following form. We have second page. It's a homological type, spectral sequence, homological type. And we have, and it's of second quadrant of this form. So minus n something, it's over cohomology. It's n Tor. It's positive number. It's negative number. And it's a number of Tor, and this is grading because it's second grading because all our models here are graded between these two things. It's modulus over this module over this algebra. It's graded modulus over graded algebra without differentials, and it converges to the sum. Sum n plus star. Maybe no. Minus n plus q. Over a. Is differential graded Tor? No, and in fact, what does it mean? It converges. It converges in weak sense. This means that we have some filtration here, and quotient of this filtration is isomorphic to infinity page. But maybe this filtration on target, maybe it's not complete or something like this. So it's because this filtration is not finite, at least because filtration, its quotients lies on diagonal, and because we in the second quadrant, any diagonal may be infinite. So any filtration may be infinite, and we cannot, in general, we cannot control the convergence. Well, what the intersection of all elements of filtration in the target. So it's kind of, it tries to converge to Tor. It's infinite page. So it's kind of with goal or target spectral sequence. So in fact, you have filtration on the target. Your infinity page is quotient of filtration, but maybe this filtration target, maybe it's not exhaustive or not complete, something like this. Today I will give sufficient condition when it converges truly. Okay, but okay, such thing. And what the topological means, why it's important in fact in topology. First of all, you can learn this you can study this from Fedya Velekjan's spецкурс, yes, on this semester, of course. But now I give some quick applications. Maybe topology. For example, yes, where it arises in topology. Consider fibration, and change of base. It's fibration, and this another base and some f, and we consider induced fibration with the same fiber but with the new base. It's f, it's kind of hat, it's p prime, I don't know. Now then, consider our differential graded algebra will be cochain algebra. For any topological space, you have cochains with cup product, and cup product. It's so cochain algebra became differential graded algebra with cup product. It's not commutative. It's not even graded commutative, but it's associative and with unit. By simplicial formula for cochain product. So in fact, we have these algebras. We have differential graded algebra of X, differential graded algebra of E. And these two maps gives differential graded algebra morphism from cochain of B to cochain of X and cochain of E. And so these things are modules of a cochain of B. And you can consider tensor product of these modules of this algebra. So in fact, our A is this, and our M and then these things. It's differential graded modules over this differential graded algebra. No, and you can define this map. On the first, it's p prime, no, on cochains, not on homologies. No, product with f hat. And this map, you can check this that this map correctly defined on tensor product and it goes to this thing. And no, yes. And in fact, this is map of CB modules. If you can define CB module structure here by any of this composition, and this is map of CB modules. Oh, maybe no. Sorry. Blah, blah, blah. This is not commutative, so this is just abelian group. So this is map of abelian group because tensor product is not module. Sorry, it's just morphism of abelian groups. And this is spectral sequence of abelian groups, of course, because in general this is not commutative and it's just abelian groups. No, and then if you have such thing, you can consider, for example, how I want to compute something like, okay. I want, for example, what if I want to compute something like differential graded Tor of this thing? Then I want to consider some proper projective resolution of one of these factors. So, for example, for left one, if I have proper projective resolution, it's proper projective resolution.
Wait, can you repeat why is it true that Cx is a module over CB?
Because we have a map of rings. It's two rings, two algebras, and it's algebra homomorphism. And then this algebra is module of this algebra.
And there we use P.
And this is P, yes.
So we use two different maps to define.
Of course, from B to different Cs, yes. It is two modules. Yes. But you can incorporate this in one thing, and then you have think to this one thing, to this abelian group. No, more or less, correctness of this map is more or less commutativity of this diagram. Okay, so and then you have, as we define differential graded Tor, we need to consider this is resolution of differential graded mode. So we have a vertical differential, internal differential in each module, and horizontal differential is differential of resolution. So we consider total of this B complex. And in fact, we can define from this map, we can also define from total. It's just, total is sum of diagonals. And in each diagonal, I have, what I have, it's Cx, and this is my resolution, okay? Horizontal is resolution differential, and vertical is my internal differentials. And total is sums of diagonals. If I consider each one diagonal, I send all these elements to 0 and only this one element to this element. And this is my map, okay? This is kind of extension of this map. If I have this resolution, then I have this map. Okay. In each summand, in each diagonal, I consider the last summand, and it goes to something in the last column. And all other on diagonal goes to 0. So what I want to say is that map of resolution defines you map from total complex to this complex. And there's also map of complexes. And then, if you have map of complexes, you can consider composition. This is identity on the second factor and this map on the first factor. In fact, this argument so far works for any commutative diagram of commutative square of topological spaces. But here is theorem. It's Eilenberg-Moore theorem.
Sorry, why do the other sums go to 0.
No, it's definition of this map. If I have a map of resolution, I define this map in this way. So theorem, if this square is not just commutative square, it's square of induced fibrations. So if this is P is fibration, and this is induced fibration, no, and for simplicity, it's simple fibration. So monodromy is trivial. It's trivial monodromy. It's action of fundamental group of base on fibers. Then this map is quasi-isomorphism. It's quasi-isomorphism. No, it's isomorphism on cohomology of chain complex of abelian groups. Then this is quasi-isomorphism. No, of course, it's not obvious, but it's true. It's more or less Eilenberg-Moore spectral sequence when they придумали their spectral sequence to study things like this, I think. So so we obtain that if we consider the homology of the thing, it's by definition differential graded Tor of these modules. So this theorem just means that this map induced the following isomorphism of differential graded Tor. And the cohomology of induced space. And so, Eilenberg-Moore spectral sequence. No, so from topological point of view, you have this induced map, and maybe you know this homology, this homology, this homology, and you want to study this homology. And this is what Eilenberg-Moore spectral sequence does, because under this theorem, we obtain that Eilenberg-Moore spectral sequence has the following form. Eilenberg-Moore spectral sequence. Now, for simplicity, for simply connected space, it's when it's converged. I will say it at the moment on lectures, when it truly converges. Then we obtain, and monodromy is trivial automatically. Then we obtain that, we have Eilenberg-Moore spectral sequence what here. And this is our differential of modules. This is our target. It's isomorphic to this thing. And the second page, it's ordinary Tor between homologies of these modules, but it's homology of X and E. So our spectral sequence starts with ordinary Tor of a homology of B, homology X and E, homology. And converge to this thing, but this thing is isomorphic to homology of induced thing. No, it's B-graded Tor because it's graded thing, and with some kind of minus second quadrant. For example, if X is a point, yes, then F star E is just a fiber. No, yes, and maybe, no. I'm not sure, maybe it's true over, no, maybe this theorem of Eilenberg-Moore true over field. I'm not sure. No, yes, maybe, no, I'm not sure, maybe it's this, no, this theorem that this is isomorphic, maybe over field, okay? Let's, for simplicity, it's over field. General Eilenberg-Moore spectral sequence works over any graded, over any ring, but no, in topology, let me assume that it's a field. Then over a field, we have this spectral sequence topological case. And for example, if X is a point, then induced vibration of a point is just trivial vibration with fiber. total space, and we obtain that we have Tor over cohomology of you have just one fibration with fiber F and simply connected base, and then you have spectral sequence from Tor over homology of B, just homology of point, then homology of total space, converge to cohomology of fiber. So this spectral sequence gives you an information about the homology of fiber if you know homology of total space and base. Third spectral sequence starts with homology of base and fiber, gives you information about total space. And this is kind of opposite direction. If you have no information about base and total space, it gives you information about fiber. For example, it's important, for example, in our two favorite cases, when E is contractible. For example, if it's some X, and this is path fibration, then it's loops. This is contractible, so we obtain this spectral sequence. This is X. If we know homology X, we obtain some information about homology of loops. No, and another case when it's classifying space of some group, and so it's also contractible, and we obtain, if we it's BG, from homology of BG we obtain homology of G. No, it's we already know from third spectral, but this is kind of new information. Also, maybe I need to say that in fact, you can define multiplication in this situation. In this case, in topological case at least, you can define multiplication of the spectral sequence. This spectral sequence would be multiplicative, not because it's homology, it has multiplication. And in fact, you can define multiplication on these terms, on differential on graded Tor, and in fact, this spectral sequence is multiplicative.
This is our second sheet.
Yes. Yes, second.
It converges by.
If B is simply connected, then it converges truly. It's maybe I will discuss it at the lecture today. Yes. No. Yes. But yes, this Eilenberg perspective, in general it converges to Tor of this thing. But by this theorem, this is this.
By what theorem? There is some.
No, this is general Eilenberg-Moore theorem, which we proved. It's just about that this thing converges to differential graded Tor. And theorem of Eilenberg-Moore say that this differential graded Tor is isomorphic to homology of induced vibration as abelian groups.
Is some other theorem?
No, yes, of course. This is not obvious. It's our topological Eilenberg-Moore theorem. No, it's what I defined this long composition. This was quasi-isomorphic. It's the same thing because it's quasi-isomorphic, because cohomology of this total tensor on something is by definition this thing, and on the right I have cochains of this thing. And quasi-isomorphism means that it's isomorphism on cohomologies. Cohomology of this tensor product is Tor. Cohomology of cochains of F star E is cohomology of F star E. It was this theorem about that such some concrete map is quasi-isomorphism. For example, easy example. No, not topological maybe, but easy example, algebraic. What if we have some differential graded algebra, but with cohomology, for example, for simplicity, it's extra algebra in one generator. No, maybe it happens. Now then, let's consider этот самый Eilenberg-Moore spectral sequence. Eilenberg-Moore spectral sequence, for example, it's of a field, and for example, consider for trivial modules. M and N are both equal to K. So I want to consider Eilenberg-Moore spectral sequence of a homology of A, K converges to homology of differential Tor, K. No, even in fact, maybe here also no, Mn no, more or less acyclic. So we only have homologies in zero gradient. So maybe homology of A lambda x, homology of M and N are K in zero. So it's no, and let X in some dimension. In some dimension, I don't know, to M minus 1. No, then, no, in fact, no, we know this Tor. This Tor must be in dimension, no, it's minus, okay. It must be second quadrant. And on this second quadrant, second page, minus n k, it's Tor n k of this sort. What is nk? No, n means that we consider n Tor. So minus n. Rho is n Tor. And k is grading. In this thing is graded nth Tor because it's also graded abelian group. But we know this Tor. How to compute? No, in fact, no, for example, I don't know. No, let's for simplicity assume that, for example, I don't know, k of characteristic 0. Then we have Cauchy-Theorem resolutions, and we know that in fact this thing is kind of polynomials. No, maybe in degree. In degree, kind of, I think in degree 2m. I'm not sure. 2m. I think something like 2m. Yes. No, yes. No, because differential of x is my yes. No, because our Cauchy resolution is kind of this thing. Cauchy resolution of k. Yes, with differential, with the Theorem differential, no, sorry, y. With the Theorem differential, which goes dy is kind of something like x. And this is acyclic, no, this is exact sequence, and it's zero grading is k. So it's free lambda x resolution of k. So y in dimension 2n, yes, 2m, because this resolution differential increase dimension. So what I obtain? I obtain that if I want to compute, no, I obtain that in degree m Tor, it's 2m, only one 2m no generator here. I have k here in degree 2m. Okay, it's clear. I think we did not discuss it before, but no, it's about grading. So I have this. This is, if you wish, it's algebra with this differential. The zero gradient is k. In fact, it's acyclic. No, because it's kind of Cauchy resolution, and we consider it's contractible. We consider homotopy for this differential. You can check that it's acyclic. No, it's easy to see from this. So, no, more or less the only cycle is co-boundary. So it's resolution. It's resolution of the gradient. You have your resolution of the following form. You have polynomials. It's graded thing. You have 2m lambda x. Now this differential increase this gradient in y by, I don't know, by m, by 1y. So it's, I think, star minus 1. No, if I consider, no, yes. X. Here, this gradient is gradient in resolution. It's just it's just number of y in my monomial. So its gradient in my polynomial is just with this gradient, where it's unit. Here, it's true. It's true. Grading as differential. I don't know. As no as no yes no as no, I don't know. No, as graded model maybe something like this. Yes. Okay. No, so what I want to say that in degree m, what I have in degree maybe stop. No, maybe even I don't know. It's just extra algebra in some dimension m. It's not important that it's odd. No, then what the Tor k? Tor k. Tor. I don't know. Tor n Tor k of extra algebra. It's isomorphic. No, it's minimal resolution. No. After tensor with k, it will have 0 differentials, and I obtain just m. With kind of k y n. Whoa. But also, no, because sorry, it is not true. Because x has internal gradient m, then y must be internal gradient m plus 1. Or m plus 1. Yes. Something like this. No, maybe this is m minus 1 for example, then it's of degree m. And so in degree n, or in degree k, I obtain this is km in fact. Yes, or something like this. It's y degree k, or something like this. Okay? No, it's k. It's just k in vertical coordinate km in one-dimensional vector space. Because my Tor is one-dimensional, and what I want to say that I have internal grading, and this internal grading, in fact, this grading, because no, if I consider this B complex, in this B complex, no, grading of y must be something like m. No, I'm not sure m plus 1 or m minus 1, no, something like this. It's something about m. And then if I compute k Tor, it's k homology. It's just k part of this resolution. No, it's generated by power of m, k power of y, k power of y, and so it lies in internal degree km. So k Tor have only one dimensional vector space in internal degree km. So in this I have only such things as n and k. If n, then n and m. Sorry, n m. No, if m is kind of my resolution, m minus 1 is x. No, so what I obtain that I have 0, then I have m 1, then I have 2m, and so on. Such one-dimensional vector spaces. And then I want to say that there are no differentials here by dimensional reasons. No, there are no differential exactly of this form. They can't be happened. No, this is как это? Very. Тут я уже не знаю, как сказать. Very. Честно говоря, я даже. Ну, it's. Ну, наклон это slope, а вот высокий или низкий, как сказать, в общем. Very high slope, I don't know, very big slope of this line. And so differentials cannot act on this line. If you start from this line, you obtain not this line. And if you want to go to this line, you must start not from this line. So if, yes, okay, yes, this part. So all differentials are 0. And so we obtain that this spectral sequence degenerates. And so in fact, this is infinity page. And again, from this part, in each diagonal, only one element of this line. So in each diagonal, so in each quotient, infiltration on this part, each quotient, each filtration is one term filtration. Yes. So I want to say that if you have degeneration, and then it's isomorphism. what I want to say. Okay. So we obtain that if you have two acyclic modules and some algebra which has homology as extra algebra, then in fact this differential graded Tor is just this thing, which we know. It's kind of this, one-dimensional in some dimension. So it's, yes, it's B-graded, and if you consider this as B-graded, then it has one-dimensional k in each degree divided by m. Okay? Something like this. Topologically, it's, for example, situation when you have two acyclic space and one space with homology as, homology of sphere or something like this. Okay. Okay. Mm-hmm. No, yes. Only zero homology. Okay, and maybe the last. Think about topology. Sorry. We have dual Eilenberg-Moore topological interpretation. It's not about fibration, it's about group actions. I will not. Let me just formulate it. It's following thing. If we let we have let's have following situation. We have G is some. Maybe. Yes, I think that G is just some topological group. Maybe compact. I'm not sure. And then this is principal G bundle. So it's a fiber bundle with fibers G, where G is structure group and it acts by left multiplication on fibers. And also we have some action of G on some topological X space X. Then we can consider Borel construction. We have action of we have action of G on X and on Y, but one important assumption that with respect to one of these actions, this is just principal bundle. So, for example, it's free action and so on, free and proper action, for example, on something like this. Then, and we also have Eilenberg-Moore theorem of the following form. We can consider we have chain complex of X and chain complex of Y, but now G X on Y and on X, and so chain complex of G, it's algebra because we have multiplication on G. It's Pantregin algebra, and it's X, so it's module over this algebra, and we can consider something like this. And we have map from this to the chain complex, to quotient. It's more or less.
How do we multiply?
How multiply what of what? G and X?
Yes.
Because we have action G of X. If you apply chain complexes, and here, for example, if you apply Eilenberg map. It's a natural homotopy equivalence between these things. Apply action. These things naturally homotopy equivalence for any two spaces, and this is just action. Okay. It's always true. It's Q-net formal that this thing is always true for any two spaces. But now you have action. So from this homotopy equivalence, any action, any multiplication on space give you a multiplication on chain complexes.
For any two spaces,
of course.
There are some conditions.
No, of course. This is always true. This is why we have Q-net formula. This is always true. Then you have, if you need to compute homology of this thing, then homology of tensor product, it's tensor product of homology and Tor and something like this. But these two homologies always coincide. Homology of this thing and this thing, just the same thing. It's Eilenberg-Zilber theorem. You have Eilenberg-Zilber map on this and Alexander-Whitney to this. So yes, it is always true. By the same argument, CG, it's algebra. No, and again, you can consider some projective resolution of one of them, total complex, and again, theorem that this is quasi-isomorphism. Maybe, what's that about? Yes. Quasi-isomorphism. So, Tor over these things isomorphic to homology of Borel construction, and Eilenberg-Moore spectral sequence has the following form: Tor between homology of G, homology of X and Y, converges to differential graded Tor, which coincides with homology of Borel construction. For example, if X is point, if X is a point, no, then it's K. This is exactly Y quotient modular G. For example, if it's vibration, in fact. So again, it's total space, it's fiber, and this base. So in fact, no, it's base. Okay. So for example, if Y is EG, then we obtain that it's also K. This is BG. This is G. Okay. And now you can define co-algebra multiplication. It will be maybe it will be also. No, in these situations also half algebras. In general, it's spectral sequence of co-algebras. Okay. So we have such another multiplication, such another Eilenberg-Moore spectral sequence, and one important particular case. Maybe let me. What exactly a particular case? When you have vibration of the following form. If you have subgroup, if you have Lie group, now it's compact Lie group, and you have closed subgroup, it's Lie. Then you have following vibration. What the fiber of this vibration? Now it was about group action. Now I want to apply the first Eilenberg-Moore spectral sequence only for vibration. It's vibration? What the fiber? No, it's quotient G modulo H. It's the looping of this vibration. If I apply the first, not this, the first homological Eilenberg-Moore spectral sequence for this vibration, I obtain the Tor of a cohomology of base between cohomology of BH and cohomology of point converges to cohomology of fiber. Maybe you want to compute cohomology of some homogeneous space, G modulo X. Then you have this spectral sequence between classifying space. And important thing that in fact, if characteristic K of 0, for example, or if it's P, but then your homology don't have P torsion. But no, for simplicity, then this spectral sequence degenerates always. So this is, and this is always isomorphism. No, because it's vector space, we have no extension problems here, it's just vector space, and as vector space, they're isomorphic. Yes, no, it's over K, homology over K. It's important, but then it's true. It starts from theorem of Cartan, which proved this for real coefficients, no, by the Theorem algebra. No, more or less the same thing, but by the Theorem thing. No, this is true for any group, Lie group. So it's important that it's Lie group. But then it's true. No, this is not obvious. Maybe we can check this for real coefficients, but for the Theorem algebra, it's maybe not very hard. No, from Eilenberg-Moore perspective point of view. But for general, of course, it's not obvious. It's important that this group Lie, that is Lie groups, we can consider some reduction to maximal torus and then prove this for torus, something like this. For example, it's one of way to prove this. No, because if characteristic is 0, then homology of BG and B maximal torus is the same thing over characteristic 0 because it's weight group and it's finite group, and so for characteristic 0 coefficients is the same homology more or less. And so we can reduct to torus and then prove it for maximal torus, something like this.